It's 21 to 11 on ABC Radio Perth. Nadia Mitsopoulos with you. Imagine knowing a young person who seems fit and healthy in the prime of their life, running a marathon or playing a game of footy, and then suddenly out of the blue they drop dead from a cardiac arrest. Now, I know a couple of people that this has happened to. And that is the risk if you have a heart disease called hypertrophic cardiomyopathy. And if it often goes undiagnosed, and it is genetic. So this is something that you may have and you don't know that you have it and probably don't know much about it. A Perth researcher has been trying to work out how to stop or even reverse this condition, and she's just been awarded funding from the global biotech company CSL to help her do it. Her name is Livia Hool. She's a professor at UWA and also faculty at the Victor Chang Cardiac Research Centre, and she joins me in the studio. Livia, lovely to have you in the studio this morning. Good morning.
Good morning, Nadia. Thank you for having me.
Tell us a little bit about this disease. How does it work? What does it actually do to the heart?
Yes, so it's caused by mutations in contractile proteins in the heart. It's what we call penetrance, varies enormously in that you could have two siblings in a family, both have the mutation, but one develops a very large heart, very young, and the other has virtually no symptoms or enlarged heart. And that's one of the things we research because we don't understand why they're so different. As you mentioned, unfortunately, the most traumatic part of this story is that it's the leading cause of death, cardiac death in 5 to 15-year-olds, and it often happens during exercise. So the heart gets bigger and then goes into cardiac arrest. And often that's the first indication that someone actually has the disease.
And this is something people are born with?
Correct. So it's what we call a familial or genetically inherited disease caused by mutations in at least 10 genes we know of at the moment, but you only need to have one mutation to cause the disease. And families just don't know. Unless somebody in the family has had genetic testing and is aware of it, then they may be aware and they can follow through. But the penetrance, what we call penetrance, is unknown because it can be very variable and it could be as common as 1 in 500 people. So there are a lot of people walking around that might be carrying the mutation and not know that they actually have this mutation.
That number sounds quite high.
Yes, and it could be even higher. One group actually argues it could be as high as 1 in 200.
So you're born with it. At what point, at what age does it develop? You say it's common in 5 to 15-year-olds, but how can it develop into something in one person and someone who has the same issue? It doesn't become anything.
Way, sure. So there's two groups. The young people, as we mentioned, 5 to 15-year-olds, unfortunately develop it extremely aggressively. So they will usually come in with shortness of breath or some symptoms or cardiac arrhythmias, sudden cardiac death, and it's very aggressive in this young people. Also very aggressive around puberty for young males especially, but it is common in males and females. Otherwise, in the rest of the population, it's around 40, 45 years of age that people start to develop the big heart. Sometimes it's picked up on ultrasound, on cardiac echocardiography. That's the primary diagnostic tool. But otherwise, it might be symptoms. Somebody comes in with shortness of breath or just not poor exercise tolerance. They may have abnormal ECG, electrocardiogram. They may be some of the indications.
And is there anything in their lifestyle that could trigger this?
Only one of the things we're studying is why exercise seems to be associated with this sudden cardiac death. So we're actually looking at that and trying to understand how what we call sympathetic activation or adrenaline activates the arrhythmia problems in the heart. But otherwise, there's nothing else that we know of that could trigger it. It's insidious, really. It can come on extremely unknown. It can be unknown.
Livia Hool is my guest. She's a professor at UWA and faculty at Victor Chang Cardiac Research Centre, and we're talking about, cardiac arrest in young people. I'm going to try and say it again. I got it right the first time, didn't I? Hypertrophic cardiomyopathy. And the issue is that 1 in 500 of you carry this gene mutation. Not everyone with the mutation will develop the disease, as you've explained, but of those that do, what is the percentage? So
that develop the hypertrophy?
That will die. that could die from this.
Okay.
Yeah.
So of those that develop the large heart, it's only approximately 2 or 3% that will actually die from sudden cardiac death. There are others that obviously have rhythm disturbances and require either pharmacological treatment or an implantable cardioverter to prevent them from having a sudden cardiac death.
So they would then have to treat it that way for the rest of their life?
Yes.
So how would you know you've got it?
Well, either by genetic testing. You could have a family history, a family member that's actually had a problem, and you know that it's a large heart. The actual definition of it is a large heart, hypertrophic, large heart in the absence of other conditions, or what we call loading conditions, such as high blood pressure. So these are people that turn up with a big muscular heart, but they have no other reason for having a big heart.
Okay, and then, you know, it's hard to know because, like you were saying, if it's in your family, right, you'd be mad. You would probably recommend you get tested. Is that what you say to people? If you've got a family history of this,
correct. So
go and get
screened. The first
screened.
thing you do is you go see your general practitioner, who would then refer you to a cardiologist, and then the cardiologist would do a number of tests. This ultrasound test, the echocardiography, would be the primary diagnostic test, and that, again, with history, would tell the cardiologist that this patient has a big heart and doesn't have any other reasons for a big heart except for perhaps a genetic mutation. And then they would offer genetic testing to the patient. So some people choose not to have genetic testing because part of the problem is that we don't have anything that can actually prevent the development of the disease, which is what we're working on. So you can see from a family's perspective, do I really want to know that my child has a genetic mutation if there's no cure for it or no treatment for it? So some people choose not to. Some people do, and if they do, then they have genetic counselling. But what we really need to do is find better cures or better treatments to prevent the development of the disease.
Okay, so if you can go on medication or an implant to prevent the cardiac arrest, what you're now looking at is trying to reverse this mutation.
Yeah, or trying to reverse the stiff heart, large heart. So we're working on a treatment that we're giving early before the development of the hypertrophy. That the treatment's actually preventing the development of the disease. Now that's good for people who may know that they have a family history of it and the genetic mutation, but they may be what we call phenotype negative and genotype positive, meaning they know they have a mutation but they haven't developed the big heart yet. So that would be good for those people. But with CSL, we're also working to try and see if our treatment will actually reverse the disease, because that's often when people present with the cardiologist, is when they already have the big heart.
So how are you doing that? Can you talk about the treatment?
Sure.
What are you doing?
Sure. So this is off the back of over a decade of research with my team at the University of Western Australia. We identified a way in which a calcium channel, or a protein in the heart muscle cells, actually regulate energetics in the heart. This was a new discovery. We know that this channel is important for calcium, influx into these heart muscle cells, and excitation contraction. Well, we saw the way the heart actually contracts. We knew that, but we didn't know that this actual protein also regulated the energetics. So we identified a way to regulate the way in which this protein alters the energetics. And what we do in these hearts are really what we call hypermetabolic or stiff, really high energy consuming hearts. And so what we've done is we've targeted this calcium channel and slowed that energy consumption and oxygen consumption so that the heart becomes less stiff, works less and slows down, and then the thickness in the heart, or the hypertrophy, actually doesn't go forward. So it's preventative. And as I said, we're actually working on treating these animals after they've developed the hypertrophy to see if we can reverse it.
Any early results?
Yes, we have one model where we can see some reversal. The other model, we can see some reversal after 5 weeks treatment, which is the plan we have at the moment. And what we're wanting to do with CSL is extend that out to 10 weeks and see if longer treatment will actually fully reverse the increase in heart muscle thickness.
And is the aim, once you've sort of done extensive testing on animals, would you then try and do human trials of this?
Sure.
Yeah.
So CSL is fabulous at this point for us as scientists, because we have what's called the valley of death. So we go with all our preclinical discovery research, but we need someone to partner with us to help us go to phase 1 clinical trials. And so CSL is offering this support for the next 2 years to really refine these treatments, make sure that we can definitely prevent it and reverse the disease. And then we go into phase 1 clinical trials. And that's where we look at things like safety and toxicity. We see no toxicity in the animals, so we're very hopeful that it will go through to humans. But this is similar to what's happened with the COVID vaccine.
Correct, except it's been
the same sort of safety.
But the speed of that is obviously much quicker because the entire world is working on this. Absolutely. But best case scenarios, you could then be doing human trials of this within 2 years.
Oh, well, we would be starting phase 1 clinical trials in 2 to 3 years if everything goes well, but realistically, probably 3 to 5 years.
Okay, sorry.
Once you've recruiting all the patients and looking at treatment. Yes.
This is quite exciting.
Yes. Yes, absolutely. I think so. As I said, for patients that even know they have the mutation, actually having a treatment that can prevent the development of the disease is really important. There is one other small molecule treatment in the US which is about to go through FDA approval, but that targets the cardiac contractile protein in a slightly different way, and it's mostly been very effective in very severe cases, what we call left ventricular obstruction, outflow tract obstruction. So they're very severe. We're trying to look at prevention right from the beginning.
Livia Hool, one final question, and I'm going to spring this on you without notice if it's okay. COVID and the effect on the heart. Do we know anything about that yet?
Absolutely. So one of the things that we're very keen to do is to try to increase awareness to the public and to the government as well about cardiovascular disease research in Western Australia, because we say there's a second pandemic of cardiovascular disease coming. That's for a couple of reasons. One is the rising rate of obesity, which is leading to type 2 diabetes. We know that at least 30% of 5 to 15-year-olds are obese or overweight, and that's going to be a problem as they get older. But also we know that 20% of the patients in Wuhan that had COVID-19 actually have cardiac damage. And we know cardiac damage goes on to develop heart failure, which still has a very poor prognosis. And we know half of those now, a year later, still have cardiac damage. So we're looking at a whole new cohort of COVID patients as well worldwide that will add to the 17.6 million that die every year from cardiovascular disease.
Yes, this is the issue with long COVID. Thank you so much for coming in.